In this presentation, we introduce a divergence to convergence approach for real-world image super resolution. Single image super resolution is a long-standing research topic. Given a low-resolution input image and the corresponding high-resolution ground truth, we need to recover a super resolution output. Deep learning-based methods typically use a deep convolutional network to learn the mapping relationship between the low-resolution image and the corresponding high-resolution ground truth to obtain the desired recovered image. Simulated super-resolution approaches usually use a predefined degradation method, such as bicubic or Gaussian downsampling, to degrade the high-resolution image and generate the corresponding low-resolution observation. However, when applied to real-world input images, the results are not satisfactory, because there exists a gap between simulated and real-world degradation. Therefore, to avoid the differences in degradation manner, we can use the real-world degradation manner to obtain high-low resolution and low-resolution data pairs. Thus, we can obtain relatively satisfactory results on real-world inputs. Some classical learning-based methods cannot reproduce rich texture details due to ill-posed nature. Our approach obtains different predictions of textures through a divergence stage, and fuses them in a convergence stage to obtain more accurate predictions. In fact, given a low-resolution image, there can exist multiple possible high-resolution predictions, because of the ill-posed nature. Classical learning-based methods, which learns the mapping between LR and HR directly with reconstruction loss, can usually obtain relatively smooth predictions. Therefore, we adopt a two-stage approach, with divergence stage followed by convergence stage, which can somewhat alleviate the difficulties in network learning which caused by ill-posed nature. As shown, in our approach, the input low-resolution images are first differentiated into different predictions by the tree-based divergence network. Then, the final output is obtained by fusing multiple predictions through the convergence network in the weight maps fusion manner. In the divergence network, each divergence branch has a deep residual layer as well as an upsampling module. We use divergence loss to train the divergence network, which includes L2 loss and modified triplet loss for each branch. The predictions of each branch are treated as negative, and the HR is treated as positive, to compute the triplet loss in the residual domain. And the inputs of triplet loss needs to be grayscaled and normalized before computation. The triplet loss can help to facilitate the divergence of the multiple predictions. In the training of convergence stage, L2 loss is calculated directly between the final fusion prediction and HR. Existing real-world datasets generally include double, triple, and quadruple scaling factors, including real SR and D-real SR. We supplemented the larger scaling factor benchmark for real-world super resolution, called D2C-SR. It contains a variety of scenes, such as city scenes, nature scenes, and indoor scenes. We construct the data pairs by zooming the lens of DSLR cameras. We conducted experiments on 3 different real-world datasets. As shown in the table, our method outperforms the previous methods in PSNR and SSIM metrics. In the ablation study, we find that the divergence loss and deep residual layer can individually improve the performance. Further, we apply the divergence to convergence structure to other methods. We find that the performance is mostly improved compared to the original methods, with a comparable number of parameters or less. We show here our qualitative comparison with other methods. In the example in the first row, our result recovers clearer and sharper edges, with a higher similarity to the HR texture. In the second row, the text in our results behaves more naturally and has fewer texture artifacts. To summarize, we present D2C-SR, a novel framework with divergence and convergence stage for real-world super resolution. We propose a new real-world super resolution benchmark, which has a larger scaling factor compared to existing dataset. Our approach outperforms on many popular real-world benchmarks. It can also be applied as a generalized structure to some other methods to obtain improvement.